Hello everyone, welcome back for further study of acid-base titration. Today we are going to discuss the calculation of hydrogen concentration in acid or base solution, which is a very important part in the analytical chemistry course. To calculate the concentration of hydrogen, we generally follow these three steps. First, write the proton balance equation, which is the most critical step. Second, substitute the equilibrium concentration of different forms in PBE with expression containing Ka, Kw, or distribution fraction to get the rigorous expression of hydrogen concentration, which are usually equations of higher degree and difficult to solve for undergraduates majored in chemistry. Third, to solve the equation conveniently, some terms which have little influence on accuracy of equation solution can be omitted to simplify the equation. The simplification is generally to omit one term in addition or subtraction, the rule of which is if A larger than 20b, then Y equals A plus B approximately equals A. First, we discuss the hydrogen concentration of strong monoprotic acid, taking C mol per liter hydrochloric acid as an example. According to the calculation steps, first write down the PBE of hydrochloric acid. We have known that MBE, CBE, and PBE of strong monoprotic acid are the same. That is, hydrogen concentration equals hydrochloride plus hydroxide equals C plus hydroxide. Substituting hydroxide in PBE with expression of Kw, a quadratic equation of hydrogen concentration can be obtained by term shifting, which is a rigorous expression to calculate hydrogen. Although the quadratic equation has a formula for exact solution, such a calculation with a radical sign is still complicated. Actually, when the concentration of acid is higher than 10 to the minus 6 power mol per liter, the concentration of hydroxide dissociated by water is less than 10 to the minus 8 power mol per liter, more than 20 times lower than the concentration of hydrogen, which can be ignored. Thus, it comes out that the concentration of hydrogen is approximately equal to the initial concentration of acid, which is a reduced form of equation for the calculation of hydrogen. It is also the calculation expression for hydrogen of strong acid in general chemistry in middle school and universities. Hydrogen concentration in strong base can also be calculated in the same way. Taking sodium hydroxide as an example, it should be noted that in base solution, the hydroxide is used as a basis and then converted to hydrogen. Otherwise, it is highly error-prone. Similarly, when the concentration of base is higher than 10 to the minus 6 power mol per liter, the reduced expression can be used, which is that hydroxide concentration is approximately equal to the concentration of base. The calculation method for weak monoprotic acid is also similar. Take C mol per liter weak monoprotic acid HA as an instance. First write the PBE, and then substitute the equilibrium concentration of dissociated forms by expressions with Ka or Kw to get the rigorous equation to calculate hydrogen concentration containing terms of HA. In this rigorous equation, there is a term of undissociated HA instead of the distribution fraction, which is for the convenience of further process. If HA is expressed by distribution fraction and substituted into the rigorous expression, a cubic equation of hydrogen concentration can be obtained by operations like term shifting. It is difficult for students majored in chemistry to solve this equation. If the expression under radical in rigorous equation is simplified before substituting the distribution fraction, the situation is improved. That is, the difficulty of solving the hydrogen concentration can be lowered. Now, we will discuss the simplification condition. Since the acid studied here is weak and the dissociation degree is usually small, CKa larger than 20 kW can be set as a criteria for whether the dissociation of water can be ignored. Based on material balance, we can get HA concentration equals HA plus A equals HA plus hydrogen. And further, it transforms to HA equals CHA minus hydrogen if the dissociation of water can be omitted. So, for the simplified equation, Kw is ignored and then substitute HA to get a quadratic equation of hydrogen concentration. Hydrogen concentration can be obtained by solving this quadratic equation, which is called the approximate formula. When the dissociated part of weak acid is relatively low compared with its analytical concentration, that is, C divided by Ka larger than 400, it is considered that HA is equal to the analytical concentration, further simplifying the calculation formula and leading to the simplest form. The third condition of simplification is that the dissociation of water can't be ignored if the acid is extremely weak with rather low concentration. That is, when CKa less than 20 kW and C divided by Ka larger than 400, the addition term under the radical in the rigorous calculation formula of hydrogen concentration can't be removed. Thus, it comes another approximate formula. From the above simplification process, it is found that all the simplification operation is to eliminate one term in the addition or subtraction under radical sign to achieve the reduced form. Based on the calculation process for hydrogen concentration of weak acid, there are three methods for simplification. These calculation formulas can also be applied in the case of monoprotic strong acid, weak base salt, such as ammonium chloride and ammonium nitrate. The calculation for hydrogen concentration of weak base is similar to that of weak acid. Nevertheless, it is first to calculate the concentration of hydroxide and then transform to hydrogen. All the calculation formulas for hydroxide have the same form as those of hydrogen, just substituting Ka by Kb. The approximate formula can be deduced according to three conditions derived from the rigorous equation. Take C mol per liter weak diprotic acid H2A, for instance, to discuss the calculation for weak polyprotic acid. First, give out the equation of Ka1 and Ka2, which are then expressed by equilibrium concentration of conjugate base. Write PBE and substitute the equilibrium concentration of conjugate base in this equation with expression of Ka and Kw. The rigorous equation can be obtained after rearrange the equation. If HA is expressed by distribution fraction and substituted into the rigorous expression, a quartic equation of hydrogen concentration can be obtained, which is unable to solve by common method. So, simplification is needed to get the solution. The principle is still to eliminate one term in the addition or subtraction under radical sign or in fraction. The method of simplification is the same as discussed before. First, ignore the dissociation of water and eliminate one plus sign to get a cubic equation, which is still complicated. In this cubic equation, there is still one plus sign. Based on the simplification criteria, when 1 larger than 22 Ka2 divided by hydrogen, the plus sign under radical can be removed. So the calculation here can be treated as weak monoprotic acid. Also, 1 larger than 22 Ka2 divided by hydrogen is considered as a criteria whether polyprotic acid can be treated as monoprotic acid. If taking the diprotic acid as monoprotic acid, based on the calculation process of monoprotic acid we discussed before, there are also two conditions. For weak polybase, replace hydrogen and Ka with hydroxide and Kb to get this vigorous equation. First, ignore Kw if CKB1 larger than 20 Kw, and it goes to the approximate formula. Then, omit the addition term successively to get the simplest formula of hydroxide. Finally, calculate the hydrogen based on the hydroxide. The amphiprotic substance can both give out and accept proton, so the calculation of hydrogen needs to be discussed separately. There are generally three types of amphiprotic substances. polybasic acid salts, weak acid weak base salts, and ammonia acids. For polybasic acid salts, take sodium HA as an example. First, list the Ka expression of polybasic acid. Write down the PBE, in which the equilibrium concentrations of species produced by acid radical getting or donating proton are expressed by Ka, followed by the rearrangement of equation to get the accurate formula. We can see that there are both plus signs in denominator and numerator. The simplification is necessary for calculation. Generally, the acid radical is not prone to accept or donate proton, so the dissociated amount is quite low, and the equilibrium concentration of acid radical can be represented by the total concentration to get the approximate formula. The next task is to simplify this formula by eliminating the addition term. There are several methods for simplification. Other cases of acid salts can be deduced in a similar manner. Here is a summary of calculation formulas of hydrogen for disodium hydrogen and sodium dihydrogen phosphate. It is noted that phosphoric acid is a kind of triacid. The dissociation constant of two acid salts should not be mistaken. The second form of amphiprotic species is weak acid weak base salt. For the 1:1 type, take ammonium acetate for instance. According to the process steps, first write PBE and substitute Ka and Kw to yield the rigorous equation, which is a high-power equation with the expression of distribution fraction. This rigorous equation needs to be simplified. Considering that the assumption of weak acid or weak base during dissociation is quite small, so the equilibrium concentration is treated as analytical concentration to get the approximate equation. There are both square root calculation in denominator and numerator of this equation, so the further simplification needs to be carried out. Still following the principle of if A larger than 20B, then A plus B equals A. Kw and Ka can be eliminated. The obtained final simple equation is quite similar to those of other amphiprotic species. Two amphiprotic substances not of 1:1 type, such as ammonium carbonate, ammonium sulfide, and ammonium diphosphate. The processing method is the same as mentioned before, that is, write PBE, substitute Kw and Ka, and eliminate addition in the equation. The detailed process will not be elaborated here, and you can deduce it by yourselves. Here is a summary of calculation steps for pH in acid or base solution. First, write PBE. Second, substitute KaKW or delta to get the rigorous equation. Third, simplification. That's all for today. Thank you.